Autonomous AI agents process information in continuous, high-frequency loops. To be effective, they require real-time execution. But enterprise security frameworks demand exhaustive validation checks that block execution until clearance is granted. This dashboard shows the performance metrics of ACGS-2, an architecture designed to break this bottleneck. It operates with a P99 latency of 0.91 milliseconds, meaning 99% of all requests are processed in under a millisecond. It maintains a throughput of 6,471 RPS, or requests per second, while enforcing 100% constitutional compliance. Lightweight APIs are no longer sufficient to secure high-risk autonomous systems. Stringent regulations like the EU AI Act and the NIST Risk Management Framework mandate strict, verifiable constraints on AI behavior. NIST RMF is a set of guidelines for managing and reducing cybersecurity risks. Relying on post-event auditing creates a critical security gap. If an autonomous agent executes a malicious database drop or initiates an unauthorized fund transfer, checking the logs after the fact cannot reverse the damage. State rollback on executed external actions is effectively impossible. Governance requires a verify before act protocol. This means the system must complete all security and compliance checks before the state machine is allowed to advance to execution. Achieving a verify before act protocol at sub-millisecond speeds is impossible with legacy infrastructure. It requires a complete architectural replacement of standard microservice patterns. Legacy multi-agent infrastructure typically relies on a 50-plus microservice mesh. That design creates compounding network latency with every hop and makes authorization boundaries difficult to enforce. This complex mesh often leads to state bleed. State bleed occurs when concurrent agent sessions pollute each other's memory context during complex, multi-step workflows across too many microservices. ACGS-2 collapses that mesh into three unified service pillars: the API gateway on port 8080, the enhanced agent bus on port 8000, and the analytics API on port 8082. The API gateway operates as the unified ingress point. It handles OIDC and SAML authentication, establishing the initial zero-trust boundary before any request moves deeper into the system. OIDC, or OpenID Connect, is an identity layer built on top of the OAuth 2.0 protocol. ACGS-2 moves context extraction and tenant isolation directly into fast API middleware. Middleware is software that intercepts incoming requests to parse session data before it hits the application logic. This eliminates the need for latency-heavy external session lookups. This structural consolidation results in a 70% reduction in operational complexity, driving the memory footprint for individual pods down to under 4 megabytes. This topology forces agents to communicate exclusively via the enhanced agent bus, which removes backdoor service-to-service vulnerabilities. By collapsing the architecture, ACGS-2 trades network hops for optimized in-memory operations. That reduced latency budget allows for strict cryptographic enforcement. We can trace a high-risk agent payload, like a request to execute code or modify an active policy, as it passes from the API gateway to the enhanced agent bus. This JSON payload visualization shows the identity extraction process. The system verifies the payload against a SPIF SVID. SPIF, or Secure Production Identity Framework for Everyone, is a set of open-source standards for securely identifying software services. An SVID is a cryptographically signed document that proves that identity. Every verified payload is bound to the core governance anchor, the constitutional hash, value CDD01EF066B6CF2. The constitutional hash represents the exact cryptographic state of every enterprise policy at a given millisecond. Security defaults to a fail-closed mechanism. If a message lacks this exact hash, or if the hash attached to the payload does not match the current active policy state, the bus drops the request immediately. This strict verification prevents malicious prompt injections. Prompt injections are attempts to override an AI's core instructions and overwrite the foundational roles of the system. The constitutional hash physically binds the system's runtime capabilities to a verifiable set of ethical and operational rules. High-capability autonomous systems are vulnerable to a Gödel bypass. This occurs when an AI agent learns the internal logic of its own architecture well enough to manipulate or disable its own safety constraints. To prevent this, ACGS 2 uses the Macy framework, or Multi-Agent Constitutional Intelligence. It enforces a separation of powers directly at the bus level. The executive role acts as the proposer. Agents in this role formulate actions and generate API calls. The judicial role acts as the validator. These distinct agents evaluate proposed actions strictly against the constitutional hash. The legislative role has the authority to propose amendments to the governance policies themselves. The agent bus enforces a hard-coded rule. An agent's SVID token can never simultaneously possess executive and judicial permissions. By enforcing role separation at the routing layer, the architecture prevents an agent from validating its own output. If every message requires cryptographic validation and role checking, the system must use a highly efficient routing strategy to maintain 0.91 millisecond latency. The speed is generated here, inside the 11-step message processing pipeline of the enhanced agent bus. The critical divergence point is step 6, the ML-powered impact scorer. A locally hosted Distal-BERT model intercepts the message. Distal-BERT is a small, fast, and light transformer model trained by distilling the BERT base model. It reads the intent of the message and generates a governance impact score from 0.0 to 1.0 in nanoseconds. Operations scoring below 0.8 are classified as standard bounded actions and routed into the fast lane. Fast lane traffic is handed off to Rust SIMD accelerated kernels. SIMD stands for Single Instruction Multiple Data, a parallel processing technique that allows a CPU to perform the same operation on multiple data points simultaneously. This is paired with a 10,000 entry Redis LRU cache, which stores frequently accessed data for immediate retrieval. This optimized fast lane handles 95% of all agent traffic, utilizing asynchronous fire-and-forget audit logging to clear the queue instantly. The pipeline is protected by circuit breakers that trigger after 5 failures and utilize exponential backoff. Exponential backoff is an algorithm that increases the wait time between retries to avoid overwhelming a recovering service. The 0.8 cutoff is not static. The system automatically adjusts this threshold based on real-time anomaly detection and traffic patterns. Machine learning enables a high-velocity triage system, reserving heavy compute resources for the small percentage of traffic that requires them. The 5% of traffic that scores 0.8 or higher is immediately diverted to the deliberation layer. We can see those checks mapped here in this matrix. An Open Policy Agent, or OPA, evaluates permissions using the Rego policy language. Simultaneously, a Z3 SMT solver runs a formal mathematical verification to ensure the request satisfies all logical constraints. SMT stands for Satisfiability Modulo Theories. The highest impact scores automatically trigger HITL, or human-in-the-loop workflows, pausing the pipeline for multi-signature approval. Anti-CAPTCHA analytics continuously monitor this layer to prevent agents from colluding to pass votes or bypass governance limits. This visual represents the final step of the pipeline for all decisions, the generation of the compliance audit trail. Decision logs are batched via the audit ledger service into a Merkle tree. A Merkle tree is a cryptographic structure where every leaf node is a hash of a data block, and every non-leaf node is a hash of its child nodes. The system anchors this final Merkle route to external blockchains like Solana or Arweave. This provides trustless proof of compliance for regulations like the EU AI Act. For high-risk actions, ACGS 2 provides a verifiable cryptographic record of constitutional adherence. ACGS 2 proves enterprise-scale, sub-millisecond latency, and perfect constitutional compliance are not mutually exclusive when traffic is segmented by intelligent risk triage. Operating these systems at scale requires treating autonomous AI entities as first-class principals. A first-class principal is an entity granted a distinct, workload-scoped identity and strict permissions directly on the network. Security and governance can no longer be bolted onto the perimeter of a network as an API gateway sidecar. Reliable safety requires constitutional constraints to be hard-coded into the fundamental logic of the communication bus.